My name is Kodama Taketoshi from Japan. Thank you for listening and watching my presentation. My presentation title is Understanding Bottom-up Processes on the Recruitment of Local Fisheries Resources. I will mainly talk about Japanese sardine and expectations to biogeochemical algal floats in this presentation. This figure shows yearly variation of Japanese fisheries catches from 1956 to 2015. The catches of Japanese fishery peaked in the late 1980s when the peak of Japanese sardine catches is recorded. The catches of Japanese sardine occupied about half of the total catches, and so Japanese sardine is very, very important for Japanese fisheries. When we focus on ecosystems, the Japanese sardine is a key player in the Western North Pacific. The sardines are third producers in the Western North Pacific. They prey on zooplankton, including their larvae, and sardines are preyed on by top predators such as tunas and whales. The sardine abundance depends on the success or failure of their recruitments. The adults migrate offshore in the summer and autumn and come back to Japanese southern coastal area in winter and spring for spawning. The spawning area is shown in the right figure. February and March are the main spawning months in the Pacific side, and April is the Japan Sea. These months are corresponding to the spring phytoplankton bloom, and so the sardines should use energy accumulated during the spring bloom through their recruitment processes. Several studies are focused on the relationships between blooms and sardine recruitment. Before reviewing the studies on the sardine recruitments, I introduce Japanese old expression. Someone says, when the strong wind blows, great shop will be rich. This means that when the strong wind blows, the blinds increase. The blind place shamisen, which was used cat fur. Cats decrease, and so mice increase. The mice nibble a hole in crates, and so crates will be sold well. In the case of sardine, we can say when the strong wind blows, sardine stock will be rich. In Oshimo et al. 2009, they showed the relationship between winter monsoon and sardine recruitment is positively associated in the Japan Sea. They could not show any processes between the strong wind and sardine stock, but considered as when the strong wind blows in winter, the mixing develops. With deepening the mixing layer, nutrients supply from deeper layers to the surface. Phytoplankton grows up with accumulation of these supplied nutrients, and the zooplankton will be rich, and sardine larvae who prey on zooplankton will survive richly. This hypothesis sounds good, but at least 4 assumptions remain. These assumptions, however, are supported in the computer model. The ecosystem model results show that the deep mixed layer in winter increases the phytoplankton abundance in the surface layer of spring. Then, the mortality of Japanese sardine is decreased with the increase of zooplankton density. But a question remains, how is the real ocean? Based on the real ocean observation, We could show another story on the relationship between sardine and spring bloom. That is, when the strong wind blows in winter, sea surface temperature in winter is lowering. With lowering temperature, timing of spring bloom delays. With delays of spring bloom, spawning period of sardine match the spring bloom period, and the energy efficiently transferred to sardine larvae, and then sardine larvae will survive richly. Please see the bottom figure. The yellow is spring bloom period, and blue is the sardine spawning period. The overlapping are colored green. The area of green is larger. The recruitment of sardine is better. In this study, we use satellite chlorophyll data to detect the timing of bloom. However, chlorophyll concentration is not used. This is because the interannual variations of satellite data in the coastal area of the Japan Sea was not variable. On the global scale, the satellite data are carefully and well calibrated, but we could not conclude that data are well localized in the coastal area of the Japan Sea. This is the result of a comparison of chlorophyll concentration between shipboard observation and satellite observations. The types denote observation period. It was difficult to say the relationships are same throughout the period. Therefore, we could not say the interannual variation based on the satellite is real. Here, I summarize the previous findings on the relationship between sardine and bloom. First, sardines are important fish for the local fishery as well as the marine ecosystem. Second, the physical data, for example, wind, air pressure, and mixed layer depth, shows the sardine recruitment depends on the scale of spring bloom. Third, the satellite observations are active in this century, but we have not sufficient reliable biogeochemical data in the real ocean yet. Therefore, more biogeochemical observation and data are necessary for understanding the effect of bottom-up processes of sardine recruitment and then their stocks. This means it is time to observe the ocean by BGC-argo and underwater gliders. My colleagues started to observe biogeochemical processes in the ocean using underwater gliders. This is the result of observation in spring 2020 at the fixed point in the Japan Sea. The upper panel is oxygen concentration and the lower panel is chlorophyll fluorescence. These are temporal and vertical distribution. We can see the oxygen and chlorophyll concentration varied temporarily. This result shows an underwater glider is a perfect tool to get biogeochemical data in the ocean. However, we get nervous during the glider observations. One potential problem is invisible limits in the seas. This is the map of EEZs around Japan. The lines show boundary of EEZ. This is only an example, as many conflicts are observed in the real. The shipboard observations are very limited and need permissions in the conflicted area. The gliders are regarded as vessels or submarines in some cases. If our gliders cannot control and exit the safe zone, big trouble happens, as we know. This is the news in the case of the South China Sea. The U.S. vessel or underwater vehicle is the underwater glider. This news lessons us the glider observations are not safe. We want to observe the ocean peacefully. Therefore, we need floats for observations, in particular, observation in the marginal seas. Now, we go back to the result of glider observations. We can see interesting phenomena from this observation. For example, we see the surface fluorescence. The chlorophyll concentration was not linearly increased in spring. The minor bloom occurred in the middle of March, and major bloom occurred in April. This result suggested we cannot understand the ocean well by the snapshot observation. So, we expect BGC-argo floats to evaluate the interannual and spatial variations of the scale of phytoplankton blooms for understanding the future of the local fisheries. The right figure are shown the example of our observations. These show yearly variation of nitrate and chlorophyll concentration in the sardine spawning area. These observations are snapshots, and we didn't know these are representative or not. We hope the BGC-argo helps solving this problem. To do this, high precision data must be collected using BGC-argo. I think the calibration of BGC-argo float data is one of the big problems for quantity estimation. Even salinity data using argo float shows unreal shift without quality control processes. I hope our shipboard observation will help it. This map shows the stations where the nutrient concentrations were observed with the traditional method by our institute. Our institute observed the vertical nutrient profiles at over 1,000 stations per year using research methods in the Western North Pacific. I consider the high-quality data certificates with global standard reference materials are necessary in order to improve the BGC-argo data. When we can do this, the combination of BGC-argo data and our observation data will make great progress in understanding the importance of biogeochemistry to the local fisheries resources. Now it's time to end. I summarize my presentation. First, the knowledge of relationship between bottom-up processes and the recruitment of fisheries resources are limited due to the limitation of observation and data. Previously, the biogeochemical data were only collected by ocean-going observations, but now we can get them using satellites, gliders, and argo floats. Second, high-quality and high-resolution data are required for quantitative estimation of biogeochemical processes in the ocean and forecast the local fisheries resources. Therefore, we expect the BGC-argo floats with high-quality data help understand the ocean and fisheries. This is the last slide. I deeply thank Drs. Oshimo, Sakuma, Wagawa, and Ono for discussion and preparation of my presentation. I also thank Professor Suga and Ito for providing the opportunity of this presentation. I also thank you for watching and listening my presentation.